is a program that you've analyzed. You spent a great deal of effort proving that this program only does what it's supposed to do. And you've compiled it, and it's great. There it is. Well, now that you've got that executable, you have to guard that executable like a hawk, because, of course, that's what an attacker is going to try to do, is change the executable to get the behavior they want out of it. And, for example, does this program, if you linked your program using a shared library, okay, so maybe I'm controlling who can write the executable. That's great. I'm covered. Oh, but I used a shared library. Now somebody can change the shared library on me, and they change the behavior of the program. So you have this sort of transitive closure thing that you have to analyze. All right, so in preparation for this talk, I sort of made, as I started trying to vaguely coalesce these sort of tricks that I have in my mind into a process, I came up with a vaguish waterfall model here. And so you start with your security goals, which are what are the properties about the system that you want to prove. And so you start with your goals, and from there you can do your analysis, and then once you've got your analysis complete and everything looks good, let's go try it out in the real system and see what happens. So the output of the goals section is a bunch of concrete goals that you can actually check. And I'll talk more about them, but they're going to be fairly simple, things you understand pretty clearly. Then in the analysis, you'll make sure that you'll be analyzing the program and the system as a whole to make sure that everything that you have as a goal, yeah, the system is doing that. It's meeting those goals. And then once you're done with the analysis, then you move on to the testing, and you make sure that everything works as you expected. Because in reality, oftentimes there's functional things that don't really work out. For example, a lot of programs, maybe it'll touch some resource. Like maybe some program you didn't realize all of a sudden has to read and write to the etc. directory, maybe change the password file for some obscure case. And you're stuck with it. You can't get rid of it for some reason. Well, now it's violating your process. And so it's violating your goals. And so now you're going to have to note that and either trust the program or something. So you have to note that and move on. And so what happens is you never change your security goals, but you'll find exceptions to your goals. In a real system, it's not going to be some sort of clean, mathematically precise system. You'll find, okay, here's a process, and it's doing, it's moving data, and it's violating my goal. I'm stuck with it. Now, you can't just ignore it. You have to annotate it, and it becomes a trusted program if you can, and that's part of the analysis. So what are the security goals? Basically, they're going to be high-level things. Things that are really easy to understand, and they'll basically probably be the person who's giving you the requirements will lay out the high-level goals for you, and then you'll kind of refine them and make sure that they're consistent and stuff. So they should be easy to understand, and they could be something you can test. I got some examples here on the next slide. For example, for a firewall, right? Very important piece of security software. You'll have, and this is how the Sidewinder firewall works, right? Stuff comes in from a network interface card, and it goes through a series of filters. The job of each filter is to make sure that it passes the certain checks, and then it goes out the other network side, other network card on the other side to maybe the inside of the network after it says everything's okay. So the important policy then is that that no packet can get through the system without going through each one of the filters, which I've then analyzed to make sure they're doing their job. So that's what a firewall policy would look like. Maybe another example of that would be you have a firewall, but you don't want to have the administrator interface from the outside, maybe the internet exposed high-risk network. I mean, you could, but say your policy is to not have the administrator have that interface. So that's a high-level goal, and you want to write that down and you want to analyze it to make sure that that property holds. Another system is like, say you have a multi-user system where you have data and you just want to keep things separate. I've only got space for one CPU, and I've only got 2 users, and I want to keep them separate. That's another thing. It sort of gets to that 2 buckets problem. So you want to keep the data separate between the 2 things, which may sound simple, but can be quite complicated. So when you start doing the analysis, the first thing you're going to do is you're basically going to be looking through the analysis, and you're going to be trying to find the trusted programs. Because again, the trusted programs are the ones that are going to give you the most problems. They're the ones that are going to raise the cost factor of your analysis, and so you want to minimize those. That pretty much sums up security analysis. I mean, there's a lot of architectural things you do trying to make components small so that you can do a true least privilege policy on them. But really, all it really gets down to is minimizing the number of trusted programs, because if you have small modules, then you've got much more analyzable code. So let's talk about the types of trusted programs. And the first class is the one that you expect, right? This is the program like the labeler program. It's trusted because it needs to be trusted to do its job. It's a labeler. It has to label the data correctly. So it's trusted. I'll analyze it, make sure it does its job. So that's your one class. That's the class that everybody thinks of. But the other ones, of course, are your critical infrastructure. In the later stages of this high assurance system that we were building for the government, we made a file system. And so the file system was a separate daemon that ran on top of those. We built an operating system right from the metal up several layers. And so everything was memory and objects. There were no files. But then we built a file system on top of it as a separate system. And we used the underlying type enforcement to constrain the file system so that it couldn't go randomly write willy-nilly into the MMU, or it couldn't change the storage manager and other things. So basically, there's another class of trusted program. They're providing critical infrastructure. The system developers are building those, and the operating system basically falls into that piece as well. But the bottom one here is the worst kind of trusted program. Because basically you do the analysis and you realize, oh, this program's trusted because it's going to violate my security goals, but that's the only reason it's trusted, is because it has to be trusted because it's going to violate my security goals. And you'll find that over and over again. You'll find sendmail is going to, or like FTP will all of a sudden have to touch this other directory, and it's like, well, no, that will violate my whole separation problem here. It's like, well, no, it needs to do that or it won't work. And so are you going to abandon FTP? Well, if you want a standard interface, no, you can't. So you're stuck with it. And so you then have to go to these other mechanisms I talked about. So for example, sendmail. And I was chatting with Jacques? Yes, Jacques earlier about sendmail. And there's QMail now, where they've taken sendmail and they've split it up into a bunch of smaller components. So that's a significant piece of engineering, to take this large sendmail program that everyone was sort of stuck with and break it into smaller components. But now when you have the smaller components, you can treat each resource separately and protect it with type enforcement, and you can get a much more trustworthy system in the end. And hopefully it works a lot better than sendmail. The other pattern that's often used is that wrapper pattern I talked about, where you'll take the large program like sendmail, and you'll just put another smaller trusted program that will check the critical property that you're interested in. I'm never going to analyze sendmail, but the one thing I'm really interested in, I can do this. Maybe I didn't get everything I wanted, but I can check this one property to make sure that that's okay. Like maybe there's no attachments on the mail message. So you write a small program that checks that. That sits outside of sendmail, and you've got maybe your critical thing done for your mission. All right, now in that previous slide when I was talking about type enforcement, I showed you this really nice sort of like cell-like architecture, and that sort of gets you into thinking about what type enforcement is, where you have a domain, there's a program that sits in that domain, and it has a bunch of resources, and maybe even other programs that run in that domain, but it's a happy little community, and then these tight little interfaces that you talk back and forth to other domains. That's true, but in a real system, it's really like a really messy Venn diagram where all the domains are talking to all kinds of other domains. The amount of the data, as you start looking at an operating system, and if you take each program that's critical and you put it in its own domain, and you see how much information has to flow just to get the system to work, you'd be amazed at the number of links that are to move data back and forth. So what it really boils down to is a graph problem, where you have each domain represents a node on the graph, and how the domains interact with other domains is the arc between, and then the arcs come in different flavors. Maybe you can write a file, and so that's sort of like a high bandwidth communication channel where one can move a lot of data. Maybe it's just as simple as I can write files into a directory, and now somebody else can see that that file exists.